Okay, now what happens if we change the conditions and we make them a bit harsh? And by a bit harsh, I mean that we change the nitric acid with concentrated nitric acid, we change the dilute sulfuric acid with concentrated sulfuric acid, and rather than conducting the experiment at room temperature, we heat the flask. Conditions. Since the conditions have become stronger and harsh, the phenol, all the possible positions of phenol will get nitrated. Basically, by all the possible positions of phenol, I mean that all the possible positions to which the hydroxy group, the hydroxyl group, can direct the electrophiles, and they are 2, 4, and 6 positions. So the product that we get in this case is just a single compound, and you guys will see what that is. Try making it yourself. Is basically a nitrated compound at the second carbon, at the fourth carbon, and at the sixth carbon. If we name it, the name is 2, 4, 6 dash tri nitrophenol. 2,4,6 trinitrophenol. Okay, let me tell you guys a bit about this compound. This compound is also called picric acid. It is an explosive compound. Basically, it can be used in bombs, and it was used as an explosive even in the World War II. It was used as an explosive in the World War II, picric acid. Okay, so 2,4,6 trinitrophenol or picric acid was used in the World War II, and this is also a benzene derivative, and it's explosive like TNT that we did in the previous videos. Trinitrotoluene, trinitrophenol is also explosive. Now let's go on to the next reaction of phenol, and this reaction has been frequently tested in the past papers. Basically, all the reactions of phenol are frequently tested in the past papers, so better do them very nicely and carefully. Halogenation of phenol. Halogenation. Okay, so by halogenation, you guys might think that we again need the catalyst AlCl3 or FeCl3 and a halogen, and the reaction would proceed as it proceeded in the reaction with benzene. Well, let me tell you guys one thing, that the OH group over here on the benzene ring is an activating group. It activates the benzene ring. It makes it less stable compared to just benzene. Compared to just benzene, phenol is more reactive, so we don't need any catalyst in this reaction. Just in halogenation, what we do is, the most common halogen that is used in the past papers is bromine. We just take aqueous bromine. Okay guys, this aqueous is important. This is the condition. This is the condition for this reaction, and it has been asked as well that for halogenation of phenol, what is the condition, and the answer was aqueous in the past papers. So aqueous is the condition, bromine Br2 is the reagent, and just bromine, aqueous bromine, is needed for this reaction to occur, and all the possible positions of phenol will get brominated. All the possible positions of phenol will get brominated, and the product will appear as Br, Br, Br on all the 3, 2, 4, 6 positions, and the product would be 2, 4, 6 tribromophenol, 2, 4, 6 tribromophenol. Okay, now the next reaction is reduction of phenol. Basically, it's the reduction of the benzene ring itself. If we react phenol with hydrogen gas, basically this is the reduction reaction, and by reduction in this case we mean the addition or the gain of hydrogen. What happens is that in presence of nickel catalyst, this nickel catalyst is important, and a temperature of around 420 Kelvin. Okay guys, it's in Kelvin, it's not in degrees Celsius. And if we hydrogenate this phenol with hydrogen in presence of nickel catalyst, all the double bonds in benzene would get hydrogenated, and the product that we get is cyclohexanol. Cyclo because this is a cyclic structure, and hexanol because it's a 6-carbon alcohol. Cyclohexanol is the product that we get in this case. Okay, then the next reaction is basically the reaction with acyl chlorides. Reactions with acyl chlorides. Okay guys, first let me tell you what acyl chlorides are. Basically, acyl chlorides are the derivatives of carboxylic acids, in which the for example, I have a carboxylic acid, CH3COOH, okay, the ethanoic acid. If I replace this OH group with a Cl, this OH group is replaced by a Cl, by a chlorine atom. The product that I get is known as an acyl chloride, and in this case it's known as ethyl chloride, or it's also called acetyl chloride. Well, the naming isn't that important. Now let's for now it's not important, but we'll talk about the naming in a bit more detail later. Now if I react, consider this as an acid. Okay, if I react it with phenol, okay guys, so this reaction is quite simple. This is our phenol over here. And one thing, phenols only react with acyl chlorides. They do not react with carboxylic acids directly. Okay, carboxylic acids have to be converted to acyl chlorides in order to react with phenol. What happens is that a condensation reaction occurs. The H from the phenol and the Cl from the acyl chloride, they both combine, and on combination they form a small molecule to be eliminated. A small molecule is formed. In this case, HCl is formed and removed. And when HCl is removed, a covalent bond forms in between these two atoms from where the HCl is removed. So the product that we get is basically an ester. So CH3COO with the benzene ring attached. This is our product, basically our product of acyl chloride with phenol. And this reaction that the phenol has undergone is a condensation reaction. Condensation reactions, by definition, are the reactions in which smaller molecules combine and eliminate a simple molecule, for example, the HCl, or in many cases, water molecule are eliminated, forming a bigger compound, a bigger molecule. Okay guys, so then after this, let's come to our last reaction of phenol. Basically, this is a specific test for phenol. This is a test for phenols only. Basically, a specific test for phenol. In this case, the reagent that we use is FeCl3, iron chloride. Iron chloride has a pale yellow color. Pale yellow color. When it reacts with phenol, phenol combines with iron chloride. It gives a product, and the product is somewhat like this. Benzene ring over here. The hydrogen is removed and oxygen is left, and then this oxygen is combined with the iron, and three molecules of basically there is a 3 outside this brackets, indicating 3 of each of the atoms inside the bracket, and 3 molecules of HCl are given out as a byproducts, and 3 molecules of phenol are needed in this reaction. So this is basically the equation, and in this case the color change of the final color of the product is purple. So the test is yellow to purple for positive phenol. So the positive test is change of the color from yellow to purple. So the final color change is yellow to purple. Well, the equation isn't that important because I've never seen an equation being asked on this. But yeah, the color test, the reagent is important. The reagent is important and the color change is important. If phenol is present, the color changes from yellow to purple. So this is important, and you guys must learn this if you don't want to learn the equation. Okay, but this is an equation to clear your concepts that how does this work. So this is how it works. Basically 3 molecules of the phenol, they combine with the iron, replacing all the 3 molecules of hydrogen, not hydrogen, the chlorine atoms, the 3 chlorine atoms, and removing the 3 hydrogen atoms from the phenol, forming this compound and the HCl molecule. This compound is purple in color and FeCl3 is pale yellow in color. So okay guys, that's it for phenol. Basically these are very important reactions of phenols, and meet you guys in the next video. And basically the next video is gonna be on carboxylic acids. So okay.